Large language models have billions of parameters, and they have been trained on trillions of words. But sometimes a 50-word prompt is all it takes to unlock their full potential, boosting performance by 2 to 3 times. That's the magic of prompt engineering. In this video, not only we will cover the essential of prompt engineering and various prompting techniques, but we will also explore a real-world case study in Python where we design and implement different prompting strategies and compare their performances on a particular task. Let's dive right in. If you're new to large language models, I would highly recommend checking out my earlier video on LLM fundamentals. It covers key concepts like autoregressive modeling, the difference between foundation and instruct models, and much more. That background will help you get more out of today's topic. I would like to start with some examples where LLMs are doing great on their own. Brainstorming ideas. Everybody knows that LLMs can be the best brainstorming partner. CV enhancement. If you're trying to highlight your key skills and tailor your experiences into a particular job description, LLM can just be a great help there. Or if you need writing feedback, LLMs can just spot grammar issues, style improvement, and can generally help you with your writing, make it more clear and impactful in general. And most importantly, or interestingly, coding assistant. If you're a developer, LLM can just probably be a great senior peer programmer at your side. They can generate a code from description. They can help you with debugging your code or refactoring. While LLMs excel in these areas, there are certain applications across the industry where they might struggle without additional guidance or techniques. Let's explore some examples. First example would be applying LLMs to perform legal document analysis and contract review. LLMs should be able to extract key clauses and terms from different contracts, and also maybe identify potential risks or conflicts in legal agreements. There are many reasons why LLM might fail in this domain. Lack of jurisdiction-specific knowledge. Legal requirement can vary significantly between different jurisdictions. The other reason could be misinterpretation of legal jargon. Legal language is highly specialized and context-dependent. Another example would be using LLMs to perform automated content moderation to maintain a safe and respectful online environment. In this case, LLMs could help us identify potentially harmful content, hate speech, explicit material, misinformation, assess the severity and the context of the flagged content, and suggest appropriate actions. LLMs can struggle with this task due to several reasons. Cultural and contextual nuances. What's considered offensive can vary greatly between cultures and contexts. The other reason could be sarcasm and subtle rule violation. LLMs may struggle to detect subtle form of bullying, harassment, or misinformation. How do we help LLMs overcome these challenges? There are generally 2 approaches: in-context learning and model adaptation. In-context learning includes techniques like prompt engineering and retrieval augmented generation. These methods work within models' existing knowledge and capabilities. We basically try to use better structured prompts or additional context or information to guide the model output. In model adaptation category, we have techniques like fine-tuning and reinforcement learning from human feedback, or RLHF. These approaches actually modify the model itself using additional data. In this video, we are focusing on prompt engineering. Prompt engineering involves crafting and refining prompts to get the most accurate, relevant, and useful responses from large language models. Different prompts can significantly affect the outcome, even when dealing with the exact same underlying information or task. That's why we have to adjust our prompt a few times or add some context to get LLM generate a more useful response. The key elements that make up an effective prompt. A well-crafted prompt may contain some of the following components. Context, which set the stage for the interaction with LLM. The task, which defines what exactly needs to be accomplished. And we might have some instruction, which provides specific directions on how to complete the task. We will definitely have some input, which is technically the specific information or query to be processed. And we might have some formatting instruction, which specifies how the output should be structured. And optionally, we might also include some examples which demonstrate the expected type of response. Here is an example prompt incorporating all these elements. Please note that the only mandatory parts here are task and input. The task is translate English idioms into French, providing literal translations and explanations. And what is the input? The input is, it's raining cats and dogs. All other components here are optionally provided to improve the quality of the response. To achieve the best result with prompt engineering, we require a methodical and iterative approach. Let's walk through the prompt engineering lifecycle together. First, we define the task and outline what needs to be accomplished. Second, we design an initial prompt based on some of the elements that we discussed earlier. Then it's time for evaluation. We will see how we are doing so far. And based on that result, we will revise the prompt as much as possible, as many times as possible, until we are satisfied with the result. And this process is called prompt tuning. And once we are satisfied, we can deploy and implement this prompt in our application. Now, let's take a look at some of the most widely used prompt engineering techniques. We're going to look at techniques like few-shot learning. This technique provides examples to guide the model's responses, helping it to understand the desired output format and style. Context prompting. This method involves providing relevant background information or context to the model, enabling a more informed and accurate responses. Persona prompting. By instructing the model to adopt a specific persona or role, this technique can tailor the tone and perspective of the response to suit particular needs. Chain of thought. This approach encourages the model to break down complex problems into smaller ones or into steps, often leading to a more logical and explainable output. And self-consistency. By generating multiple responses resulting from different reasoning paths, we select the most consistent one, and this technique can improve reliability of the responses. The most effective way to learn about all these different techniques would be applying them to a real-world case study. In customer service, efficiently categorizing and routing customer inquiries is crucial for providing timely and effective support. First, let's understand why this might be a difficult task for LLMs. Well, there is a lack of company-specific knowledge. LLMs are trained on general data, and they may not understand specific products, services, or internal categorization of the system. Second, inconsistent interpretation of priorities. Without proper guidance, LLMs might not consistently gauge the urgency or importance of issues. So the problem is we have a lot of customer service tickets. We want to use an LLM to route them into the right department by auto-tagging them using one of these 6 tags that we have here. We will start simple by a basic strategy, which is also called zero-shot approach. In this method, we provide the model with the task description without any examples. That's why it's called zero shot, because the model hasn't seen any specific examples before. For instance, we might say, classify this text into one of the following categories. This approach relies on model's pre-existing knowledge only to complete the task. Our next strategy would be few-shot learning. Here we provide the model with a few examples of the task before asking it to perform on new data. A few-shot prompt might include examples like, the password reset link isn't working, and I'm logged out of my account. I have an important presentation in an hour, and I need immediate access. This should be categorized as technical support. This method helps the model understand the task better by seeing some concrete examples. One quite interesting idea on the top of few-shot would be contrasting examples or contrasting few-shot. So the whole idea here is, in addition to providing the correct category along with explanation of why that category is correct, we could also add explanation why other categories are incorrect. So this is going to give the model a lot of information that potentially it can use for tricky or complicated cases to avoid making mistakes. It's just 3 examples in this case, but it could be we actually use the exact same number as few-shot learning. So with few-shot learning, we are hoping that the model will figure things out. Another way of doing that would be by actually concisely providing that concrete background information and context to the model so it can use that when it comes to processing a query. So in this particular case, we might have our own definition, company definition of different categories that might be different for different product or company or organization. What we can do is we can actually define all those 6 categories or tags as a context and provide that to the model. But one problem with context prompting is that it can really get wordy, or you might not exactly know what to put there as a context. This is where persona or role prompting comes in. We ask the model to assume a specific role when prompting. This works because we are implicitly providing context and behavioral cues that will guide the model's output. Let's see an example. We might want to say, you're an experienced customer support working at a tech company. Your job is accurately categorizing customer inquiries to ensure they are routed to the correct department. You have years of experience and understand the nuances of customer communications. Our next strategy is chain of thoughts, sometimes referred to as step-by-step reasoning or complex task breakdown. This strategy encourages the model to break down its own thinking process or the original problem into smaller problems or steps. Completing those small tasks often would be a lot easier than the original complex problem. We might actually break down the original task of categorizing the customer service tickets into 3 steps: identifying the main topic in the ticket, determining the user intent, which might be different from the actual topic, and then matching it with the closest or the most relevant tag. We could also combine different prompting strategies to guide the model better. So this might get a little bit tricky as we need to be careful not to overwhelm the model, which I'm going to explain later. But combining a few different strategies together often can work to your advantage. In order to put those prompting strategies that we came up with for the auto-tagging problem, we need to also pick a large language models. I'm going to borrow from the Flan family from Google. And as far as it comes to the variants, I'm going to pick a mid-range Flan T5 large, which has 780 million parameters. So let's code this up. First, we need to import the necessary modules from the transformers library. Then we're going to specify the model name as Google Flan T5 large variant. And then we're going to load the pre-trained tokenizer that is going to convert the text input into the numerical representation. And then we're going to load the pre-trained model. We also need a function to evaluate performance of different prompting strategies for this problem. But what kind of problem do we have here? This is a multi-class classification problem where we try to correctly classify customer service ticket using one of the 6 tags or classes that we have. Therefore, the best metrics to consider here are going to be precision, recall, or most importantly, F1 or Jakarta index. Now, the way we're going to code this up is going to be iterating through all the test data, creating a prompt using one of the strategies that we came up with, tokenizing that prompt and generating output from the model, and then decoding that output and inferring the prediction label. It's finally time to check out the results. We're going to look into each strategy and their performance and see what we can learn from it, starting with basic zero-shot learning. 41%, not too bad. Well, if we consider random guess as our baseline, with random guess for 6 category, you will get 16.6. So this is much better than random guess. So nothing to complain about, but we will see if we can get better result with other strategies. Next in line is few-shot learning. Nice. Few-shot learning actually gave us a significant improvement. By providing examples, our model actually performed about 20% better. This is a huge jump and shows the power of giving models concrete examples to learn from, and the model did learn from those. The next strategy that we're going to look at is contrasting examples, where in addition to the correct answer for each example, we're also going to tell the model why not other categories. So a lot more information. It didn't work. So interestingly, when we introduced negative example, our performance dropped slightly compared to few-shot approach. This suggests that while negative examples can be helpful in some contexts, they may have introduced confusion in this case, or they might have overwhelmed the model with so much information that our model could not digest. Okay, let's take a look at the context strategy next. Nice. So context strategy actually gave us another 2.2% improvement. This is quite significant because it tells us if you already have some concrete context that we can feed it to model directly, it might work even better than few-shot learning. But on the other side of the thing, if we could have provided a lot more examples, maybe the result of few-shot was but better as well. But again, we're seeing the power of both approaches here. Next strategy that we tried was persona. And this is very significant. So persona prompting got us around like 58%, which is quite close to few-shot, a little bit lower. And so this is interesting because persona prompting is a quite easy strategy to implement. You don't need to come up with a lot of perfect, concrete, hard examples. You don't need to be super careful with what kind of context I'm providing. You're just gonna give the model to play a role or act like a certain character. And that gave us a lot of improvement already, and that's amazing. Chain of thought was the next thing we tried, and interestingly enough, it didn't quite work a lot in our case. Part of the reason could be that in our data set, the tickets are pretty short. They don't have lots of information. So breaking this down into steps probably requires a lot more context and information in the ticket itself. But in our data set, the tickets were pretty concise. And then what other thing we could try here is the combination, mixing different strategies, or let's say mixing strategies that are working quite well. Let's say if we combine persona with context, wow, that's pretty interesting. 73%. So that's by far one of the best results that we have ever got. So not only giving the persona, but actually enriching that with some context got us the best ever result. Now, building on this, now that this is working, why not adding few shot on the top of that? And this was quite interesting. Well, I tried with all different combination, and the best result that I got for this particular case was persona, context, few shot. So combining persona, context, and few shot together got us the best results, in this case, 78%. So we can see that with proper prompt engineering, we can actually improve the result by, in this particular case, we boosted the results by 2 times, from 40% to 78%. So that's the power of prompt engineering. What we have covered so far are the primary, most fundamental prompt engineering strategies. There are many more strategies out there, and new ones are being introduced every month or every week based on one of these strategies that we have covered here today. And out of all those examples out there, one noteworthy and very interesting example is actually self-consistency prompting, also referred to as multiple pass reasoning or ensemble prompting. This involves asking the model to approach the problem from multiple angles and then aggregate the result. This is closely related to chain of thought prompting. The only difference is that this is an alternative to the greedy decoding reasoning in the chain of thought, which we're only going to follow one pass, most probable next token at each step to generate a response. Here we consider multiple different passes and we aggregate or do a majority voting. Today we use metrics like precision, recall, and F1 to evaluate performance of our different prompting strategies. However, if we were working with applications where we want to actually look at the quality of the responses from a linguistic perspective, then there are a bunch of other options most popular out there that we can use. I just want to briefly mention this for. Perplexity reflects the model's certainty in predicting the next word. BLEU assesses fluency and grammatical accuracy. Coherence measure how well the text flows and makes sense internally. Relevance gauges how closely the output matches the given prompt. Today, we looked at prompt engineering to maximize LLM's potential. However, prompt engineering is not your only option out there. If your application requires up-to-date or specialized knowledge, you might consider looking into RAG. If you need consistent adherence to a specific guideline or ethical standard, RLHF might be the best option. And if you demand highly specialized language or domain expertise, then fine-tuning might be the thing that you want to be looking into. Let's wrap up here by taking a look at the pyramid of approaches. At the base, we have prompt engineering, which is the most accessible option in the sense that it requires minimal resources and data. We always start with prompt engineering, and if the result is not satisfactory, we can look into other options such as RAG. RAG is still considered an inexpensive option, but it requires a well-structured knowledge base that we have to create. And the other 2 options here are going to be RLHF, which is more expensive than RAG, but not as expensive as fine-tuning. However, it requires human preferences and some human feedback data. And finally, on the top, we have fine-tuning, which adapts the entire model to a specific task. It demands a large and high-quality data set and requires significant computational resources. As you can see here, as we move up the pyramid, we generally see better performance, but that comes at the cost of increased data requirement and computational complexity. The key is to choose the right approach based on the specific need, resources, and complexity of the task. And that's all for today. Thank you for watching. I will see you next time.